Behind me is a very interesting geometrical result. It's called the Incenter-Excenter Lemma, and it's super powerful for many difficult geometrical problems. So here is the statement. We have a triangle A, B, and C, and we're going to draw its circumcircle, which is the circle that passes through all three of its vertices. Now, from vertex A, I'm going to draw the angle bisector of this angle. So it's this purple line over here. And I'm also going to draw the other two angle bisectors from B and C, which I've drawn with dotted lines, as you can see, right? So the three angle bisectors of a triangle in fact meet at a point called the incenter, which I'll call I. Now, I'm going to also consider this point L, which is the intersection of the circumcircle and this angle bisector. Now, the Incenter-Excenter Lemma states that if you were to consider the circle which passes through B, I, and C, i.e. the red circle over here, if you consider this red circle, then this point L is exactly the center of that circle. Now you might be thinking, well, that's kind of strange, right? I mean, what should this point have to do with this red circle? Like, why is it exactly the center? And that's why this theorem is so notable. Now, you might have just clicked on this video to watch the theorem, or to know the theorem, I should say, but the proof is often way more applicable and way more useful than the actual theorem statement itself. However, the proof for it is much more important and much more applicable to many other problems. So let's get right into it. Before delving into a proof, we should always try to simplify the problem, maybe translate it a little bit so that it's easier to tackle. So if L is indeed the center of this red circle over here, then we must conclude that BL, LI, and CL are all equal in length. So I'm going to write that down. We need to prove that BL is equal to IL is equal to CL. And this is obvious because these 3 points are on the circle. So therefore, the distance from the center to each of these points must all be equal. So now that we know what we want to show, let's actually proceed. So firstly, I'm going to consider this angle over here, okay? So this angle over here is angle CBL. So I'm going to label that angle CBL. And notice that this angle over here is actually inscribed within the same arc, which is LC, as this theta angle over here. So because they're both inscribed within the same arc, they must be equal. So this angle over here is also theta. And I can label that over here. This is theta. Now, again, consider that this angle over here, so angle BCL, this angle is, well, inscribed within arc BL, and this angle, theta over here, is also inscribed within BL. So therefore, they must both be equal. So therefore, this is theta. Now, notice this. Because we have a triangle, BCL, and because there are two equal base angles of theta, then this would mean that BCL, well, this triangle over here, is an isosceles triangle with BL is equal to LC, right? So we have proven that BL is equal to LC because these two base angles are equal. Now this is becoming pretty close to what we want to prove over here. I'm actually going to put a box around here to show that we have not proven this yet, just to not get confused with what we've written over here. So we need to show this, but we're getting there, right? So how do we prove that IL is equal to either one of BL or CL? Because if we can prove that, then this would mean that this equality chain holds. Well, to do that, we're going to introduce a new variable. I'm going to let the angle, or the variable, alpha denote this angle over here. So so this is angle IBC. So angle IBC is equal to alpha, my new variable. Now notice this. Because this is alpha, and because BI is a bisector of this angle over here, right? Then this angle over here is also theta, not theta, alpha, right? So angle ABI is also equal to alpha because it's literally an angle bisector by definition. Now, because this is alpha, right, and because we have a triangle BIA, right, then this would mean that the sum of the angles add up to 180 degrees. So what is this mystery angle, right? This mystery angle over here. Well, this mystery angle is equal to 180 degrees minus theta minus alpha, right? Because sum is 180. So this is equal to, so angle AIB, sorry that this I is, covered up, but AIB, this is equal to 180 degrees minus theta minus alpha. Now, because notice that this angle over here is equal to 180 degrees minus theta minus alpha, then this angle over here, being the angle that completes the straight line angle, must be equal to 180 degrees minus this entire thing. So I'm sorry that I pointed at this first, but it's 180 degrees minus angle AIB. That's what I meant. This is what this angle is. So that's equal to exactly angle BIL. So this is angle BIL, right? And therefore, if you were to do the calculations, this would fall out to be theta plus alpha. Notice that because we have an angle over here equal to theta plus alpha, and because we have an angle over here which is equal to theta plus alpha as well, and because it's in a triangle, then therefore, because the two base angles are equal, this would mean that BL is equal to LI. Notice that I moved I out of the way. So BL is equal to LI. And therefore, since BL is equal to LI, what does that mean? Well, because BL is equal to LC as well, then this is equal to LC, which is equal to CL. So I'm just swapping the letters. But notice that we have exactly proven our desired result. We have proven that BL is equal to LI is equal to LC. So therefore, there must be a circle passing through these 3 points with center L. Okay, I've added more to the diagram, as you can see, and that's because the Incenter-Excenter Lemma has more to offer. This one will be left as an exercise for you to prove. So here is the setup. We're going to extend the line segment IL beyond point L over until we hit the red circle, which I'll call this point IA. And note that I'm actually extending a full 180 degrees, okay? So it's a straight line. Now, here is the setup. If we were to consider extending the line segment AB beyond point B, and extend the line segment AC beyond point C, like I'm drawing, then here is the theorem. If we were to consider the exterior angles over here, so I'll label this a very big angle, right? If I were to consider this angle and connect this point B to IA, so connect this point B to IA, like so, then this line BIA actually bisects this large exterior angle. Similarly, if we were to take this large exterior angle over here and connect this IA to C, then this line segment CIA also bisects this large angle over here, which I'll actually mark with 2 ticks because I already used 1 tick over here. So, can you prove this? Well, this will be left as an exercise. So yeah, I hope you found this video interesting. If you did, please do consider dropping a like and subscribing. Thank you very much. Bye.